Hello, everybody hear me okay?
Yes.
My name is Stian. I'm from Trondheim, Norway. It's a little town up north where I do front-end web development for a company called Beck. And today I'm going to teach a little bit about math and how it relates to some of the things we do in JavaScript. And especially to the thing we call transforms. Transforms are used in various places throughout the web stack. We use it in the graphics with CSS, SVG, WebGL, Canvas. It's also used somewhat in other areas, but we're going to focus on the graphics bit. Transforms, they enable us to alter the position and the shape of objects. We can move objects around in space. Whoops. Yep, there we go. We can move objects around in space and we can scale them. We can rotate and we can even skew or shear objects. We can use one of these transforms or we can combine them in various ways. And we can use this to give our objects new shapes or throw them around the page or things like that. But what's actually going on underneath here? We can observe the effect, we can use the functions, but what's actually happening under the hood here? Why does an object morph into that exact shape when a transform is applied? Why does the application of a transform give different results when applied after another transform rather than just by itself? And in order to figure this out, we have to take a look at some math. And the first thing in the math world we're going to look at is the matrix. I'm not talking about the movie, but rather the mathematical concept. A matrix is a rectangular array of values. It's arranged in rows and columns. Matrices have many usages, and they form the basis of a lot of computation and calculations. They even have their own calculus. But in this particular context, the transform is a matrix. The underlying representation of a transform is actually defined as a matrix. And when we are doing transforms, we are actually applying a matrix to the coordinates of a point through matrix multiplication. And this way we can produce a new set of coordinates for a point and get a new location. And when we apply transforms to objects, we are actually transforming each of the points that define the object using the same transformation matrix. And when the points that define the object change their location, the object changes its location as well. So to take a look at the mathematics behind this, when we want to map from one set of coordinates to another set of coordinates, we are doing this with matrix multiplication. The coordinates of a new point is defined as the multiplication of the transformation matrix and the original point. Like this, it looks probably a bit daunting, but we can break this computation down into 3 pieces. The first piece is the formula that defines the new x location of the point. And we can see here that we take the first row of the transformation matrix and we dot multiply it with the original point. And dot multiplication is taking each element and each element of the 2 rows and multiply them, and we then add them up. And we can repeat this for the y portion of the coordinate and for the perspective component. And we now have the complete set of equations that we need to solve in order to get the new location of a point after a transformation. But after the previous slide, you might have some questions percolating in the back of your heads. Why do we have 3 values defining the point in a 2-dimensional space? And why is the third component set to just 1? When dealing with computer graphics, we use a representation for coordinates called homogenous coordinates. in this representation, we include a value to represent the perspective component of the canvas. And when you're varying this, this value, what we're actually doing is we are either shrinking or scaling the canvas up. But this does not affect the relative distances within the canvas itself. So to keep this, the things ordered and easier to deal with for ourselves, we usually keep this component at the value 1 at all times. You might also wonder why we're actually using 3x3 matrices. Wouldn't it make more sense to use 2x2 matrices for two-dimensional transforms? The reason is that in order to do the translation transform, that is moving an object around in space, we need to have one more column than we have dimensions. This means that we need 3 columns to do a 2D transformation, and that's also why we have 4 columns when we do 3D transformations. And the matrix calculus says that we can only multiply 2 matrices if the second matrix has the same number of rows as the first matrix has the number of columns. And this is also where the homogeneous coordinates come in, because homogeneous coordinates have 3 rows, so you can use them with a translation matrix that has 3 columns. And you might also wonder why the third row in the transformation matrix is set to 0, 0, 1. This is basically to avoid messing with the perspective component of the homogeneous coordinate. As I said, we want to keep this value at 1, so if we keep the third row of our transformation matrix at 0, 0, 1, this is what we achieve. And in most cases, we don't really want to fiddle with the perspective component at all. In fact, none of the low-level native 2D matrix APIs exposes the ability to manipulate this row at all. So the second piece of the puzzle is the coordinate system. The coordinate system forms the context for our transforms. And the way most coordinate systems are laid out when working with web graphics is to place the origin of the system at the top left corner. What this does is it allows us to define all the points within this system with positive x and y components. And this way we don't have to deal with negative coordinates unless we want to enter outside the context. The origin of a coordinate system decides the coordinates of a point, which is kind of natural. The coordinates of a point then decides what the outcome of a transform will look like. Here we have a box, and the lower right corner of the box is located at 65, 65 within this particular system. And if we apply a scale transform to this point, we see that the box moves and the coordinates move accordingly. And also the box increases in size. If we, for instance, would change the origin slightly, for instance, to the middle of the box, we get a different effect when applying the same transform. This effect is not entirely unexpected because we did actually change the coordinate of the lower right corner when we also changed the origin of the coordinate system. And I mention this because in the different models we have for doing graphics on the web, we have different ways of setting the origin of the coordinate system. In CSS, we place the origin relative to the object in question, and it's in the middle of the object by default. But in Canvas and SVG, the origin is placed at the upper left corner of the container to the object. So now that you have seen a bit about the theoretical foundations of transforms, we can look at let's revisit the shorthand transformation functions I showed at the very beginning and how they relate to the underlying matrix representations. One useful way to think of matrix representation of a transform is to compare it to like the hex code of a color. We can do some things using only the shorthand colors, for instance red. But if you want to have like a slightly bluer red, we just have to change the hex code. And we can do the same thing with transforms. We can unlock the real power and freedom if we access the underlying matrix representation instead of using the shorthand transforms. So the first transform you want to take a close look at is the translate transform. And the translation transform works by adding a set value to the existing value of either x or y coordinate. And these values are located in the upper two rows of the third column. As you can see here. And the effect of such a transform is pretty straightforward. If I go here and, for instance, change this value, you can see that the box moves in the x direction. And similarly, if I change this value, the box will move in the y direction. The second transform is the scale transform. The scale transform works by multiplying the value of either the x or the y coordinate by a factor. And you can see the scaling factors are located at the diagonal of the transformation matrix. And when we are changing the scale, the coordinates of the point is multiplied by the scaling factor and resulting in the object increasing in size along the x-axis or the y-axis. In this particular demonstration, I have placed the origin of the system in the center, so that when I change the numbers, the box is scaled along the appropriate axis. Next up is the rotate transform. The rotation transform works by moving both the x and the y component of a point, either clockwise or counterclockwise, by a value. And this value is decided by the trigonometric functions in the upper left part of the matrix. And these functions are chosen in such a way that when we rotate, we are moving the point along the edge of a circle, which has its center at the center of the coordinate system. And the same here as the last one. I have put the origins of the system in the center, so when I change this, we get a nice rotation effect. So a positive value is clockwise, and a negative value is counterclockwise. The final transformation shorthand is a bit of a strange one. It's the skew transform. It's also known as the shearing transform. This shorthand is actually not available in Canvas or in SVG, but CSS has it. And the way this works is by moving the x-coordinate of a point by a factor of the y-coordinate. So, and then vice versa for a y-coordinate. It's very similar to the scale transform, but instead of scaling along the same axis, we're scaling along the opposite axis. And the way we decide this factor is by using the tangent function. This is because we want to move the x or y component of the coordinate in such a way that the angle of the new position relative to the opposite axis forms an offset of the value. It's a bit hard to visualize, so we can do this demonstration thing. If I change the value of the skew in the x direction, you can see that all the x points, positions of the points move a little bit to the right. And this way, all the lines that used to be parallel to the y-axis are now shifted to the right by 17 degrees. And the same thing applies in the y direction. But now we have seen how single transforms affect an object independently. But what if we want to apply more than one transform to an object? What is the outcome of the composition? And to answer this, we first have to take a look at some of the properties of matrix multiplication. One of the great things about matrix multiplication is that it is associative. This means that applying multiple transforms to the point is the same as applying the product of all the transforms to the point. And what that means is that the combined transformation matrix can be calculated upfront, which can save us a lot of work and is way more performant. And in this way, we can also do an easy inversion of the transform. But we need to remember that matrix multiplication is not commutative. This means that the order in which the transformations are applied matters. A then B produces a different outcome than B than A. And this is different from normal numbers where 2 times 3 is 6 and 3 times 2 is also 6. And this is one of the reasons that large complex transforms are harder to reason about. So I'm going to illustrate it with an example. This is the calculations for calculating the combined transform of a scale and then a translate. And if we look at the row-column pairs that define the translation part of the final matrix, you can see that it's 30 along the x-axis and 30 along the y-axis here. And it's because we end up with the number 2 from the scaling transform and the 15 from the translate transform are multiplied and produce 30. But if we reverse the order of these transforms, we get a different outcome. Here we can see that the number 2 from the scaling transform no longer lines up with the translation part of the first transform. In this way, we end up with the transform of a translation of just 15 in the final product. And this goes for the y-axis as well. And when you do this with a lot of transforms, the product just gets harder and harder to reason about. So this is one thing to have keep in mind. And to wrap this up, here's a quick summary. The transform shorthands we see in web graphics, like translate, scale, rotate, skew, and such, are actually shorthands for matrices. And these matrices define the way we map from one set of coordinates to another set of coordinates. And when we compose transforms, we are actually doing a matrix multiplication. So remember that ordering matters here. And also a quick note about three-dimensional transforms. The math is pretty much the same. The perspective component is has more to say because we actually have perspective. But all the same principles apply, all the same concepts apply. We have one more dimension, so naturally there's more math, not just more complex math, but just more. So taking the knowledge from two-dimensional transforms and scaling it up to 3, it's actually pretty easy. Thank you for having me.